We're going to begin this video by actually using some of the properties that are outlined in the theorems that we just did some proofs for to be able to simplify and help us solve some problems here. So for my first one, A, it just is asking me to simplify. So if I was to rewrite that out, so I've got 4 plus 2 times vector u minus 10 times vector v. So those are scalars. And I got 5 times 2 times w plus v minus u. And so we can go to some of the properties that we identified to help us simplify this. Now first, this 4 plus 2, obviously, that's kind of silly. That should be written as 6. And that just then becomes 6u minus 10v. And here I've got this 5. Now this 5 I can distribute through. So I would end up with 5 times 2, which gives me 10 w plus v minus 5u. Now from here, I can actually simplify a little bit more with that 10 in front of the w plus v, because I've just become 10w plus 10v minus 5u. Now I'm going to essentially collect like terms or collect the vectors that are the same. So I'd have 6u minus 5u. That would just leave me with 1u. I've got negative 10v plus positive 10v. Well, those essentially just cancel each other out. And then I'm left with 10w. And there's no other w's to need to be collected up with it. Now, for my next question, though, it gives us some information and asks us to find something. So the information it tells us is that w is equal to u plus v. U dot v equals 4, and v dot w equals 7. And what we want is the magnitude of v. Okay, well let's see if we can rewrite this. So remembering things like here I've got, well, I could say v dot w. And we know that equals 7, but what I could do is I could say, well, here's this w, and I could rewrite it as that w up there. So I could say v dot, and then that becomes u plus v. All right. And then remembering that we know v dot w is 7, so I could just say 7. And from our properties with dot product, we saw that we can distribute the dot product into the sum and end up with v dot v. And this is the same as, remember, the dot products are commutative, so I can switch that around. And when you take a dot product with yourself, that just becomes the magnitude squared. Now, we have from the information above that u dot v is equal to 4. So we're able to fill that in as well. Now I can simplify that to say that 3 is equal to the magnitude squared. Remember, we're looking for the magnitude. Well, I can just take the square root, and then I'm left with my magnitude of v. So that's just some ways we can apply these theorems. I'm going to go on to our next section that is going to talk about the cross product. So again, you'll recall that I had mentioned that we kind of have 3 different types of multiplication. We talked about scalar multiplication and dot product, and now we're coming to what we call cross product. So now the idea of cross product has to do with areas and parallelograms. So when we have a vector u and v that are non-zero, we're actually able to kind of extend those vectors and form a parallelogram. And we're able to then identify the angle theta between them and take the angle theta here as our height, using the angle, we're able to find our height and then find actually the area of this parallelogram formed by the two different vectors. Because if you'll recall, the area of a parallelogram is base times height. Well, if we take our base to be the magnitude of u, our height here is the magnitude of v times sine of theta. All right. So if we have this as our area, we can actually rearrange it. And so following this proof as much as you'd like, we can find that our area of our parallelogram could actually be determined by taking the product of the magnitudes squared and subtracting the dot product squared. Now this works right here for this area right here is best for best for vectors in 2 dimensions. So what we have here, oh, and one more thing is if either of the vectors is 0, then obviously there's no area, and so the formula doesn't work. So let's look though and try to determine our area. So recall from the previous page that the area will be u, magnitude of u squared, magnitude of v squared, minus u dot v squared, taking the square root of all that. Well, I need to find my magnitude of u. So that'll be the square root of -1 squared plus 1 squared, which will give me square root 2. Need to find my magnitude of v. So that'll be 2 squared plus 3 squared, which will give me 4 plus 9, so that's 13. And then I need my dot product, u dot v, which will be, what, -2 plus 3, which will give me 1. So now if I put these all together for my area, I'll have square root, well, that'll just be 2 times 13 minus 1, which is the square root of 26 minus 1, square root of 25, which is equal 5. And I would say then that the area is 5 square units. So that's great that we have a formula that works best for R2, but we were talking about this idea of a cross product. And so we're going to introduce that idea now in 3 dimensions. So before we can get there, we need to identify these vectors called the I, j, and k vectors. Now the I, j, and k vectors are the standard unit vectors along the different axes. So like I is on the x-axis, j is on the y-axis, and k is on the z-axis. And it's our standard unit vector. If we were to find the magnitude of each of these, they would be equal to 1. And so the idea is that I can take any vector and I can in R3 and I can rewrite them in terms of I, j, and k. And so what I would write here for vector v is that I have 2 times vector I minus 3 times vector j plus 4 times vector k. So now what is the value there? Well, we'll show you as we come along. So we're going to talk about this idea of a cross product. So the cross product of u and v has the following properties. And just to emphasize, always look what world we're in. We're in R3 right now. So the magnitude of the cross product is actually equal to the area of the parallelogram between them. Okay, that's pretty cool. We also have that the vector u cross v are orthogonal to both u and v. So when I find u cross v, I'm actually getting a vector as a result. So my cross product gives me a vector. So we haven't actually defined the algebraic way of finding the cross product yet, but unlike the dot product that gives you a scalar, the cross product gives you a vector. Now, if we think about two vectors, u and v, and we talk about finding something that's orthogonal to both of them, there's going to be more than one vector that's orthogonal to both of them because of direction. And so the idea is that we have this right-hand rule where u cross v is in the different direction than v cross u. So if I have like u here and v, and I have my angle theta, then, I would say u cross v, and this is just my interpretation of it. So u cross v would go in one direction, and then v cross u would go in another direction from it. All right, and so bearing in mind that we would be looking at this in 3 dimensions, but I just want to emphasize how the different, it's not like the dot product that will give us the same whether I go u dot v or v dot u. We're actually going to be getting a vector in opposite directions. Now, we actually can consider, if you recall, our I, j, k vectors that we had before. We can go in the direction of the circle to remember quickly the cross products of these standard vectors. And this can help us because it can help us say, oh, if my vector is in I and I'm crossing it with a vector in j, then it tells us if I'm going to get a vector in the positive direction of k or the negative direction of k. So if I was going to do the cross product of I, jj, or kk, what ends up happening is I end up with 0 here. And that's because you have to recall that in these cases, I would say that the parallelogram has area of 0. And that's what was going on there. Now, following in a clockwise pattern, ij will give me k, jk gives me I, ki gives me j. But then if I'm going counterclockwise, what ends up happening is I end up with these negative vectors. And that's how we're able to kind of tell whether or not we're going to get positives or negatives. But let's remove ourselves from there and actually figure out how to do a cross product. So remember that we're looking at doing cross products only in R3 right now. And our cross products are given with the following formula. Now, this formula, you're more than welcome to memorize, but I've actually provided, I like to use just a simple way of lining them up to help me find this. So then I go v1, v2, v3. So I start by putting both vectors on top of each other. I put the vector that comes first on top, the vector that comes second underneath. And then to actually find my cross product, and I'm going to go to highlighter, I go, okay, I need to find the first one. So I'll cross out the first column, and then I go and multiply and subtract. So I cross out the ones, and I'll go u2 times v3 minus u3 times v2. and that becomes my first component. I then go and I'm going to cross out my second column, and this time though I start the other way. So with the first one I started and I went left to right. This time I go right to left for the second time. So I go U3V1 minus U1 V3. And for the third one, I do come back and I go left to right. So I just have to remember to switch it when I do the middle one. U1 V2 minus U2 V1. Now that might have been a little hard to watch. Watch me do it with the next example. Okay? So I want U cross V, so I'm going to go 1, 2, negative 2, 3, 0, 1. Line them up on each other. So using highlighter just to help see it, I'm crossing out. I'm not looking at the first column because I'm looking for the first component, and then I'm going to go right to left in a diagonal. So that'll give me 2 times 1 minus negative 2 times 0. And that's going to be my first component. And then my second component. This time I just have to remember when I'm doing the second one that I go right to left, not left to right. And so remember the first column, it's like you act as though it's not crossed out anymore. So we take the greens off. And this time I go with what's not crossed out, and I'd have negative 2 times 3 minus 1 times 1. And now I go to the third, and again, I cross it out. Oops, I wanted that on highlighter. And I act as though like the other ones haven't been crossed out at all, and I go left to right. So I'll go 1, 0, minus 2, 3. Okay, so that gives me what? 2 minus 0, negative 6 minus 1, and 0 minus 6. And I now have this vector. We could also though notice that if I took U and I did the dot product with this, 2, negative 7, negative 6, or V and did the dot product with this, 3, 0, 1, both of these cases my answer is 0. And that is a way to show that what I did for the cross product is actually correct, because the cross product gives me a vector that's orthogonal to both, and it's orthogonal if the dot product equals 0.